theorem is basically, I mean, it's basically like characterizing compact sets of R, of Rn, right? That's what we have understood now, kind of, right? So Bolzano Weirstrass theorem, we are using it as a model to understand compactness in metric spaces, right? In some sense. And we will understand it completely, I mean, in mathematical sense. Yeah. Yeah. So Bolzano Weirstrass, it starts with something which we know. Yeah. But in the end, I mean, basically we saw that P equivalent to Q, that basically tells you that Bolzano Weierstrass is just saying that the compact subsets of Rn are those which are closed and bounded, right? That is what, okay? So Bolzano Weierstrass is saying that compact is same as closed and bounded. Of course, in Rn, this doesn't apply to arbitrary metric spaces, okay? I'm not delving into counterexamples a lot, but I will have to at this point. Counterexample is another game. There are books called Counterexamples in Topology, which are written. So because the book itself is called Counterexamples in Topology. You might have heard of it. But anyways. Now the concept of locally compact, which is essential to understand. Okay, let me define it this time in a different way. Okay, and later at some point, if you can understand that both are equivalent, that is up to you. But I will not show they are equivalent. I'll define it in a different way now. Okay, slightly different way, very slightly. Okay, yeah, I should not say different, just slightly. So locally compact, in our case, maybe I should, yeah, I should define it like this: that yeah, X be a metric space all the smaller balls are compact at some point, then that implies that it is, yeah. So I think this is good enough. So X be a metric space. Yeah, X is locally compact. Through this, we are learning many things, because soon you will be looking at like Arnab set sequentially compact, and then this compact, that compact, paracompact. Paracompactness is a very important concept, but we will see. Yeah, but that doesn't apply to metric spaces, because in metric spaces all these concepts are same. But yeah, but see, the point is, why is it that these concepts which are about distances, think about this, I will not talk about it but right now, I mean, but to think about it, I mean, why is it that the concept about metric spaces, why is it, I mean, if there is something like that beneficial, why is it beneficial to study these concepts in places where there is no metric, where there is no sense of distance? Why is it beneficial, I mean, to study it outside? Yeah, that you can think. It's related with something. You have to, it's an opinion question kind of, right? So with some examples and so on. But X is locally compact. I wrote it twice. Yeah, if given any point P, okay, there exists a natural number N depending on P. Okay, so there is natural number, there is a radius, okay, and such that these balls of radius P, sorry, balls around P of radius NP, their closures are, I'll change it, sorry, yeah, radius M are compact for all m bigger than or equal to np. So you see what I'm talking about, right? I'm saying that given any point p, there is a small enough, I mean, I'm sorry, yeah, I should say 1 by m, of course. I mean, that's what I meant, but yeah, yeah. Given any point p, after some point, all the balls uh, become compact. Okay, all the balls of radius. It's true for it. Actually, something else is more is true, but this is to begin. Okay, is it? So given any point, is small enough radius, if you go, then there those balls, those closures of the balls, of course, because open balls are not compact. I mean, the boundary of the ball is there, which are limit points, but they are of course not in the set. So of course you have to take closure, no doubt, but they are compact, and that's why locally compact. Okay. Yeah, I will agree that this definition is not doing complete justice to the thing of locally compact, and probably you are reaching to go. You probably want to now go and read about locally compact spaces on your own, because there are so many things going on. So you can, you should look at locally compact metric spaces and read the topic. There are many equivalent things, but for our purposes, what I'm trying to get at is not about local compactness. So that we can. So you understand, this is the definition. Key, if around any point, if you take small enough balls, then they are all pre-compact. They're all nice. They all have that Bolzano Weirstrass. They all have that Bolzano Weirstrass. Right? They are closed and bounded, and they are compact. So they satisfy Bolzano Weirstrass. I mean, yeah, that probably the last statement is wrong. It doesn't make any sense. So this. So now we want to say that locally compact, which I was thinking in, I mean, I had doubt, but yeah, locally compact does not imply that X has BW. Now I'll just call it BW, right? This X has the Bolzano-Weierstrass property, which are this property that, as I said, or sequence property, you can say from there also. Okay? So, I mean, you understand what I'm talking about, right? Please let me know.
It's
Hello? Yeah?
uh,
Your voice broke.
Hello.
Huh.
Yeah, it's understood.
Now it's clear. Yeah, okay. Right. So now you see, if you want to go from this locally compact to this, you will see that you will not, you will see that there are problems. Okay. Here we want to prove that every set that is closed and bounded, every large, it could be large, but it's bounded and it is closed, then it is compact. Right? You want to prove that. So does this locally compact help you? So let's try to prove and see that you will actually figure out, you'll not just see that you are not able to prove it, but you will kind of see that there's nothing which you can use to prove it. It's kind of like that. You'll get the feeling, not enough sentences in the theory to go around to prove it. So basically, let's do it like this. I mean, suppose you have a sequence, right? Suppose you have a sequence, and now you want to say that it has a convergent subsequence. Okay, you want to say that it has a yeah. Just 1 minute. Getting a little distracted. Sorry. So what I'm trying to do is I'm trying to give you an intuition for why this result is not true. Okay. Yeah, I have one intuition, but if I want to say it, yeah, it's a bit difficult to finding it a bit difficult to explain this. without going into something else, that compactness is the topological property and boundedness is not a topological. Yeah, just a minute. Yeah, if you take a sequence, right? Take a sequence in this closed and bounded space, or maybe if I just if I just take a discrete set, yeah, and then that will be closed, and I can obviously make it bounded, and uh, it is locally compact. Yeah, but yeah, basically there is no reason to expect this to be true. That's the point. Okay, I will not explain this. Maybe I'll probably confuse you a little bit. Okay, so I'm not explaining it now, but I'll give you a problem which will actually you can easily do, and that will give you a solution to this. So I mean, you can just, it is a standard example. Yeah, maybe hold on. So closed and bounded, right? I mean, yeah. So basically, you look at this, right? Let X be a set. Okay, let X be a set. And what you do is you define a distance such that the distance between any 2 points is equal to 1 if X is not equal to Y, and it is of course 0 if X is equal to Y. This is a metric space, correct? This is a metric space. Okay, now show that X is locally compact. Okay, X is locally compact. It's easy to show, but but you should, of course, it may not be easy initially, and that is only because this definition is new for you. Okay, so but if X is an infinite set, show X is not compact. So I'm actually telling you everything you have to do. X is not compact. Okay, and then of course show that X is closed and bounded. X is closed. I mean, what to say? Yeah, X is closed and bounded. Means the whole space itself is closed, of course, because space is as closed as itself. Yeah, by definition, you can, and it's bounded because of the way I've defined the metric. Okay, so it fails for the very simple reason. So maybe you can just write it and try it later. Okay, and yeah, these counterexamples are very useful to have actually with you when you are doing any kinds of problems in, especially like also in exams, like this, especially the entrance exam, sometimes something is true, false, simple counterexamples work, right? So note it down. There are more interesting counterexamples, but we'll not get into them. Okay, so yeah, let me know when I should proceed. Okay,
What
now
does it mean by mod of X equal to infinity?
size is infinitely many points in the space. Okay, yeah, yeah. Please work out these examples. They are the stepping stones on which you will stand higher and higher over time. Okay, all right. So I'm erasing this. Right. Now I will need again a small notion. Yeah, and just give me a minute while you just relax. Uh, Right. Okay. So, I mean, if you kind of contemplate why is it that it happens in Rn, why is it that these kind of things happen in Rn? Yeah, you will see that in the proofs that you do in Rn for this fact that closed and bounded is compact, or or the Bolzano Weirstrass theorem, right, where you prove that every sequence has a convergent subsequence in Rn. Why does it work? Why is it that it works? Why is it that every sequence has a convergent subsequence? Can you tell me why? Why is it that in R, why does it work? Why every sequence has a, of course, R is locally compact, that is there, but why is it that every, because we proved that this property implies locally compact, right? Yeah. Has a convergent subsequence. Yeah. This is probably a deep question. You can prove it. You can probably give me several proofs if you read. But yeah. So for this, I mean, of course, you have to think. I also maybe don't know the answer. But please go over the proofs of these things. Okay. The basic proofs, which is, like there is one proof, right, which constructs a monotonic subsequence. So basically, there is one proof, right, which uses order, which takes a monotonic subsequence using the order property of R, not the arithmetic, only the order property of R, right? It constructs a monotonic subsequence, correct? And then that monotonic subsequence, and then it uses the supremum property. And this is basically completeness. This is actually a crucial property, correct? Completeness. R is complete. R is complete, right? Or it is the same thing as every sequence has a Cauchy subsequence. Okay, this same, and if you don't know why it is same, then you should know. You should just check it out. Every sequence. I mean, these are part of the standard things. You read it, or you've done it, or you read it. Okay. I mean, Arnav, I mean, you're actually doing the courses, so I mean, this probably is done in your courses. Okay. So every sequence has a every Cauchy sequence converges. Yeah. Okay. Yeah. If you think about it, one of the reasons is this, right? Order on R, and that order is there in Rn also in some way, that lexicographic thing, right? It allows you to sort of take a monotonic subsequence and then take a subsequence of that subsequence in the second coordinate and so on, right? So it works in Rn. But let's focus on R. I mean, R and Rn are not very different in what we are investigating right now. So you will agree that these two things actually allow you to say that every closed and bounded set becomes compact, right? But then the problem is that when you go to an arbitrary metric space, you see that the order property goes out of the window. It's no more there, right? You don't have order. So that actually forces you to think about this. Can you explain this thing without using order? Can you give a two-step recipe, or preferably two-step should be enough? Because see, why I'm saying two-step, because these two are sort of independent properties. Agree? Right? Having an order and then having the supremum property. And this is also true in probably lattices and whatnot. But but yeah. But I'm saying that, yeah, okay, so think of, is there some other proof that you know? Yeah, this maybe you should think about. Yeah, so see, what is it? I mean, what is it that you need? You just need that supremum you can take, because the supremum concept, Cauchy sequence concept, you can define in every the supremum, forget supremum is you cannot define um, in every metric space, but there is an equivalent property of Cauchy sequence converges or complete. You can define Cauchy sequence doesn't need order. You can define it. So you define the notion of Cauchy sequences, and so basically completeness is something which you can throw in. Correct? But what else do you throw in? Well, you have to just throw in the following, that every bounded sequence has a Cauchy sequence, has a Cauchy subsequence. Isn't it correct? It's also necessary, right? So this is the things that you throw in, that every bounded sequence has a Cauchy sequence, has a Cauchy subsequence. Okay, I'll write this on the next page. So you see how we are going about this is kind of thing works in mathematics, right? You have a property, you have an equivalent property of it, but that other equivalent property doesn't use the full structure, and that's the beneficial. It uses less structure, so you can use that property to move higher in the higher realms of generality. We can talk about them. This is how I think about these things. But let me state these two things, and then we'll get a complete characterization of compact spaces in terms of the more primitives, in terms of the more simpler concepts of completeness and Cauchy sequences. Okay, and I'll write that, and I'll not prove it, of course. That you can check out. But you see, the way we are arriving at it, I suppose that's very important. In analysis, the proofs are not difficult. I mean, the only thing you to know what to prove. Yeah, sorry, there's something came. Yeah, okay. All right. So let me get there. So are you people understanding what I'm trying to do, right? Trying to give you an understanding of this compactness business. Okay, so let me just write that on the new page. So X be a metric space. Okay, and K be compact. Okay, and now I'm giving some homework. Show that every you can use any definition of compact. Of course, K is compact in X, right? You can use show that every sequence. So again, I'll use some condensed notation. In K, okay, has a Cauchy subsequence. And this is a trivial fact because it has a convergence subsequence and convergence. But of course, you should prove it. That will be good. Second fact is K is complete. Correct or not? Yeah. You may recall this, but you should prove it also. Prove it, try it, and then maybe read if you, yeah. And after that also you can talk to me about this, of course. And this is the thing. Now, what we want to say is that, and this is a theorem which is probably not obvious, right? Claim. So this is going to be the most non-trivial thing about today. That 1 and 2 imply, okay, if if Y satisfies 1 and 2, then Y is a subspace. Yeah? So I am characterizing the compact subspaces of a metric space. Bolzano Weirstrass gives a characterization which works in Rn. That characterization doesn't work in arbitrary metric spaces, we have seen. If it doesn't even work in locally compact spaces, we have seen. I mean, it is homework. But now, this characterization always works, but this is obviously weaker, right? I mean, it assumes more things. So then y is compact. Okay, so what I'm saying is that y में क्या होता है कि every sequence, oh no, sorry, this is not non-trivial, this is actually already said, right? Yeah, I'm sorry, yeah. So y satisfies 1 and 2 means that y every sequence has a Cauchy sequence, and then because it's complete, so it will converge. So every sequence has a convergence of sequence. So this is actually trivial, right? So this is an observation. Correct? So the compact spaces of a metric space can be talked about in terms of Cauchy sequences. Okay, this is there. But I want to define a concept which is the non-trivial thing, and that is totally bounded. And then an exercise will come, totally bounded. Okay, so again, y in x is said to be totally bounded, and so one of the exercises will be to prove that it is bounded. Totally bounded if given any epsilon greater than 0, there is an epsilon net. You can put a net on the space, kind of, So I'll tell you. So given any epsilon greater than 0, there exists some points, finitely many points, that's important. This will depend on epsilon, such that if you take the balls around these points of radius epsilon, small epsilon diya, okay, it might be very small, but still you can manage with finitely many points and cover the space, cover the y, of course. Getting the point? And it should work for, so you take this and epsilon, you take 1 by 100. Still, radius 1 by 100, I mean, with that radius itself, I can manage. Okay, I can cover my space with finitely many balls. Now we are moving into some serious things slightly. Okay, these covering are very sometimes mysterious, non-trivial, get interesting. Okay, goes on, right? This. Okay, so this is property number 3. Show, hopefully I'm correct. Okay, 1 and 3 are same. Okay, and then that totally bounded and complete will be compact. Then it will follow, right? Because yeah, and that is what mathematics is about. This concept of totally boundedness is an extension of boundedness, because we are defining a concept which generalizes the concept of boundedness. Because show that such a set y is bounded. Show that y is bounded. With this property, then y is bounded. Totally bounded implies bounded. Okay? So this is a concept which we have introduced, which generalizes the concept of bounded, because it contains this concept encompasses boundedness, right? And this concept combined with completeness gives you the compact sets. Okay, why is this characterization nice? Because Bolzano Weirstrass is analogous to it. It says bounded and complete. Well, closed doesn't imply complete, but right. But yeah, closed and bounded implies complete. But yeah. So basically, Bolzano Weirstrass characterization is similar. So this characterization is sort of an analogous extension of that. That is what you need in mathematics, because you move to harder and harder places, but your theorems sound the same, and so you really don't feel like it's hard, and so you can move freely and make observations. And from analogy we learn, right? I mean, how else do you learn? How else do you make observations? I don't know. Out of nowhere, it's difficult, right? So this is the thing. And yeah, you'll find all this in those references, mostly maybe arranged in a different way. Yeah. And yeah, just I mean, yeah. So maybe if can we meet again after 5-6 minutes? Is it fine, or what do you say? for 10-15 minutes?
Uh,
Is it okay?
yes, sir.
Okay, yeah. So
It's
then,
okay, sir.
yeah, then let's take a break, relax, and then meet. And maybe 15-20 minutes, I'll just do some things. Okay, yeah. Maybe the problems. Yeah. All right. Okay. So, sorry, I stressed it long today. Yeah.